going to look at the sign test. The sign test allows us to find regions where we know that roots lie in, and we're going to look at a few motivating examples of functions where we know where the roots are, but just to demonstrate this idea. So a root, first of all, is what we need to define, and hopefully you've seen that before, but a root of a function is just where that function is equal to 0, okay? Simple enough. So the sign test, essentially, the idea is if we can find a point where the graph's greater than 0 and the point where the graph's below 0, the function's below 0, then it must be 0 at some point in between, but there's a couple of technical conditions, and that's what these motivating examples are going to look at. So this function here, we know what the graph looks like, some curve through here, and we know the roots are at 1 and minus 1, but that's not what we're going to look at for now. If we look at the point f2, f2 is equal to 4 minus 1 is equal to 3, and f0 is equal to minus 1. This is greater than 0, this is less than 0, and these points are here and say here, and we know the function has to come through some line here, so we know there's some root x1, so say x1's a root, x1 satisfies that it's between 0 and 2. Again, we confirm that because we know there's a root of 1. So can we use this test to find regions like this where we know roots exist for all functions? Well, the next example shows you one issue we might have. If we have a function that's defined like this, so it's 1 if x is greater than 0 and minus 1 if our input's less than 0, well then let's say f of 1 is equal to 1, that's greater than 0. F of minus 1 is equal to minus 1, is less than 0. Well, that means that any root, we have a root between 1 and minus 1, right? Well, no, because if we look at this graph, it's minus 1 all the way down here, and it's 1 all the way here. It never crosses the x-axis, okay? There's no roots, this graph has no roots. So what's gone wrong here with the sign test? Well, this function is not continuous, and it's an extreme example of non-continuity, but that's what you have to be careful of. So that allows us to formally state the sign test. So if f of x is continuous, and it just has to be continuous on the region that you're performing the sign test on. It doesn't have to be continuous for all x, but again, it's another technical detail that you don't need to look at right now, but keep that in mind. But yeah, continuity is important. Then f of a less than 0 and f of b greater than 0, so a and b are particular x values constants, implies there's some x1 in this region such that fx1 equals 0. Okay, hopefully this theorem makes sense. We won't look at a formal proof because you don't need to know one, but you know, this example is great for this because we know there's a point here, or any graph, we know there's a point here, and we know the function is continuous, so it can't get to that point without at some point crossing that x-axis. Okay, so yeah, there must be a root in that range. Hopefully that makes sense. So yeah, if you're asked to apply the sign test, that's what it means. If you're asked any limitations of the sign test, you need to talk about continuity. Okay. So thank you very much for watching this video. Hopefully you found it a useful lesson on the sign test. We're going to be looking at more numerical methods as we move forward, including Newton-Raphson and the like. So stay tuned for that, and I hope to see you in the next video.